Today's topic of presentation is IR spectroscopy. Introduction. One of the most important tasks of organic chemistry is the determination of organic structures. When an interesting compound is isolated from a natural source, its structures must be completely determined before a synthesis can begin. Whenever we run a reaction, we must determine whether the product has the desired structure. The structure of an unwanted product must be known so the reaction condition can be altered to favor the desired product. In many cases, a compound can be identified by chemical means. We find the molecular formula by analyzing the elemental composition and determining the molecular weight. If the compound has been characterized before, we can compare its physical properties like melting point, boiling point, etc. with a published value. Chemical tests can suggest the functional group and narrow the range of possible structures before the physical property are used to make an identification. These procedures are insufficient, however, for complex compounds that have never been synthesized and characterized. They are also impractical with compounds that are difficult to obtain. Because a relatively large sample is required to complete the element analysis and all the functional group tests, we need analytical techniques that works with tiny samples and that do not destroy the sample. Spectroscopic techniques often meet these requirements. Absorption spectroscopy. Absorption spectroscopy is the measurement of the amount of the light absorbed by a compound as a function of the wavelength of light. In general, a spectrometer indicates the sample with light. Measurement the amount of light that transmitted as a function of wavelength and plot the result on a graph. Unlike chemical tests, most spectroscopic techniques are non-destructive. That is, the sample is not destroyed. Many different kinds of spectra can be measured with little or less or no loss of sample. In this book, we cover 4 spectroscopic or related techniques that serve as powerful tools for structure determination in organic chemistry. Infrared spectroscopy covered in this chapter observe the vibration of bonds and provide evidence of the functional group present. Mass spectroscopy. Mass spectroscopy, also covered in this chapter, is not a spectroscopic technique because it does not measure absorption or emission of light. A mass spectrometer bombards molecules with electrons and breaks the molecules into fragments. Analysis of the masses of the fragments give the molecular weights, possibly the molecular formula, and clues to the structure and functional group. Less than a milligram of sample is destroyed in this analysis. Nuclear magnetic resonance (NMR) spectroscopy, covered in this chapter, also observe the chemical environments of the hydrogen atom or the carbon atoms and provides evidence for the structure of alkyl group and clues to the functional groups. Ultraviolet spectroscopy (UV spectroscopy), also covered in this chapter 15, observe electronic transitions and provide information on the electronic bonding in the sample. These spectroscopic techniques are complementary and they are most powerful when used together. In many cases, our known compound cannot be completely identified from one spectrum without additional information, yet the structure can be determined with confidence using 2 or more different types of spectra. In chapter 13, we consider how clues from different types of spectroscopy are combined to provide a reliable structure. The electromagnetic spectrum. Visible light, infrared light, ultraviolet light, microwaves and radio waves are examples of electromagnetic radiation. They all travel at the speed of light, about 3 into 10 to the power 10 centimeter per second, but they differ in frequency and wavelength. The frequency of a wave is the number of complete wave cycle that passes a fixed point in a second. Frequency representing by the Greek letter mu. Nu is usually given in hertz, meaning cycles per second. The wavelength represented by the Greek letter lambda is the distance between 2 peaks or any 2 trough of the wave. You can see also in the diagram the wavelength and frequency, which are inversely proportional and are related by the equation mu lambda is equal to c, or lambda is equal to c upon mu, where c is the speed of light, nu is the frequency in hertz, lambda is the wavelength in centimeter. Electromagnetic waves travel as photons, which are massless packets of energy. The energy of photon is proportional to its frequency and inversely proportional to its wavelength. A photon of frequency nu has an energy given by E is equal to h nu, where h is the Planck constant, which value is 6.62 into 10 to the power minus 37 kilojoule per second, or 1.58 10 to the power minus 37 Cl per second. Under certain condition, a molecule struck by a photon may absorb the photon's energy. In this case, the molecule's energy is increased by an amount equal to the photon's energy, H nu. For this reaction,
For this reason, we often represent the irradiation of reactive mixture by symbol HU. The electromagnetic spectrum in the range of all possible frequency from 0 to infinity. In practice, the spectrum ranges from the very low radio frequency used to communicate with submarines to the very high frequency of gamma rays. Figure 12.1 show the wavelength and energy relationship of the various parts of the electromagnetic spectrum. The electromagnetic spectrum is continuous and the exact position of the dividing line between the different regions are somewhat arbitrary. Toward the top of the spectrum are the higher frequency, shorter wavelength, and high energy. Toward the bottom of the low frequencies, longer wavelength and lower energy. X-ray are so energetic that they are excite electron past all the energy level, causing ionization. Energies in the UV visible range excite electron to higher energy level within molecule. Infrared excite molecule vibration and microwave energy excite rotation. Radio wave frequency excite the nuclear spin transition observed in NMR spectroscopy. First is the infrared region. The infrared, from the Latin infra mean below red, region of the spectrum corresponding to the frequency from just below the visible frequency to just above the highest microwave and radar frequency. Wavelength of about 8 into 10 ki power minus 5 centimeter to 1 into 10 ki power minus 2 centimeter. Common IR spectrometer operator in the middle of the region at the wavelength between 2.5 into 10 ki power minus 4 centimeter and 25 into 10 ki power minus 4 centimeter, corresponding to energies of about 4.6 to 46 kilojoule per mole. Infrared photons do not have enough energy to causing electronic transition, but they are caused group of atoms to vibrate with respect to the bond that connect like them. Like electronic transition, these vibration transitions correspond to destruct energy and molecule absorb infrared radiation only at certain wavelength and frequency. The position of an infrared band can be specified by its wavelength, measured in microns. A micron corresponds to 1 millionth of 110 ki power 6 of a meter or 10 ki power minus 4 centimeter. A more common unit, however, is wave number, which corresponds to the number of cycles in a centimeter. The wave number is the reciprocal of wavelength, since 1 centimeter is equal to 10,000 micrometer. The wavelength can be calculated by dividing 10,000 by the wavelength in micron. The unit of wave number are centimeter inverse. For example, an absorption at a wavelength of 4 micrometer corresponds to the wave number of 2500 centimeter inverse. Wave number have become the most common method for specifying IR absorption, and we use wave number throughout this book. The wave number is proportional to the frequency of the wave, so it is also proportional to the energy of photon of this frequency. Some reference still use micron, however, you should know how to convert these units. Molecular vibrations. Before discussing characteristic infrared absorption, it is helpful to understand some of our vibration energies of molecules. The following diagram shows that how the covalent bond between two atoms act like a spring. If the bond is stretched, a restoring force pulls the two atoms together towards their equilibrium bond length. If the bond is compressed, the restoring force pushes the two atoms apart. If the bond is stretched or compressed, then they release the atom vibrate. The frequency of the stretching vibration depends on the masses of the atom and the stiffness of the bond. Heavier atoms vibrate more slowly than lighter one. For example, the characteristic frequency of CD bond is lower than the lower than that of CH bond. In a group of bonds with similar bond energy, the frequency decreases with increasing atomic weight. Stronger bonds are generally stiffer, requiring more force to stretch or compress them. Thus, strong bonds usually vibrate faster than weak bonds. For example, oxygen-hydrogen bonds are stronger than carbon-hydrogen bond. So, oxygen-hydrogen bond vibrate at faster frequency. Triple bonds are stronger than double bond. So, triple bond vibrate at higher frequency than double bond. Similarly, double bond vibrate at higher frequency than single bond. In a group of bonds having atoms of similar masses, the frequency increases with bond energy. Some common type of bond together with the stretching frequencies to show how frequency varies from the masses of atom and strength of bond. An infrared spectrum is a graph of the energy absorbed by a molecule as a function of the frequency or wavelength of light. The IR spectrum of methanol is shown in figure 12.2. In the infrared region, absorption generally results for the exciting the vibration modes of the bond in a molecule. Even with sample compounds, infrastructure contain many different absorption, not just absorption for high bond. The methanol spectrum is a good example. We can see the broad OH stretch around 3300 cm inverse, the carbon hydrogen stretch below 3000 cm inverse, and carbon oxygen stretch just 1000 cm inverse. We also see absorption resulting from bending vibration including seizure and twisting vibration. In a bending vibration, the band length stay constant but the bond angle vibrate about the equilibrium value. Bond stretching frequency. In a group of bonds with similar bond energy, the frequency decreases with increasing atomic weight. In a group of bonds between similar atoms, the frequency increases with bond energy. The bond energy and the frequency listen here approximately. Carbon hydrogen bond energy for 20 bond energy bond stretching frequency 3000. Carbon OD for 20 2100. Carbon 350 1200. Now the frequency with bond energy. Carbon 350 1200 1200. Carbon with double bond, carbon double bond 611 1660. Carbon with triple bond 8040 2200. Consider the fundamental vibration mode of water molecule in the following diagram. The two oxygen-hydrogen bond can stretch in the phase with each other symmetrical stretching, or they can stretch out of the phase anti-symmetric stretching. The HOH bond angle can also change in bending vibration, make a seizure motion. Stretching, symmetric stretching, anti-symmetric stretching, bending, scissoring. A non-linear molecule. A non-linear molecule with an atom generally has 3n-6 fundamental vibration mode. Water has 3 fundamental vibration mode as shown in the preceding figure. Methanol has 12 fundamental nodes and ethanol has 21 fundamental modes. We also observed combination and multiple overtone of the simple fundamental vibration mode. As you can see, the number of vibrations in the infrared spectrum can be quite large even for simple molecule. It is highly unlikely that the IR spectra of two different compounds will show the same frequency for the various complex vibration. For this reason, the IR provides a fingerprint of a molecule. In fact, the region of IR spectrum containing the most of these complex vibration is commonly known as fingerprint region of the spectrum. The simple stretching vibration in the 1600 to 3500 centimeter inverse region are the most characterizable and predictable. Our study of infrared spectroscopy will concentrate on them. Although our introductory structure or study of IR spectra will largely ignore bending vibration. You should remember that these absorptions generally appear in 600 to 1400 centimeter inverse of the region of the spectra. Experienced spectroscopists can tell a great deal about the structure of the molecule from various kinds of bending, vibration known as ringing, sizzling, rocking, twisting that appear in a fingerprint region. The reference table of IR frequency list both stretching and bending characteristics of the characteristic frequencies. IR active and IR inactive vibration. Not all the molecule vibration absorb infrared radiation. To understand which one do and which do not, we need to consider how an electromagnetic field interacts with a molecular bond. The key to the interaction lies with the polarity of the bond, measured in as its dipole moment. A bond with dipole moment can be visualized as a positive charge and as a negative charge separated by a spring. If this bond is placed in an electric field, it is either stretched or compressed depending on the direction of the field. On the component of an electromagnetic wave is a rapidly reversing electric field. This field alternatingly stretch and compress a polar bond as shown in figure. When an electric field is in the same direction as the dipole moment, the bond is compressed and the dipole moment decreases. When the field is in the opposite dipole moment, the bond is and the dipole moment increase. If the alternate stretching and compressing of the bond occur at the frequency of the molecule, natural rate of vibration, energy may be absorbed. Vibration of bond with dipole moment generally result in IR absorption and said to be IR active. If a bond is symmetrical and has zero moment, the electric field does not interact with the bond. For example, triple bond of acetylene has zero dipole moment and the dipole moment remains zero if the bond is stretched or compressed. Because the vibration produces no changes in the dipole moment, there is no absorption of energy. This vibration is said to be IR inactive and it produces no absorption in the IR spectrum. The key to an IR active vibration is that the vibration must be changed in the dipole moment of the molecule. In generally, if the bond has a dipole moment, its stretching frequency causing an absorption in the IR spectrum. If the bonding is symmetrical, substituted and has zero dipole moment, its stretching vibration is weak or absent in the spectrum. Bond with zero dipole moment sometimes produce absorption because molecular collision, rotation or vibration make them unsymmetrical part of the time. Strongly polar bond may absorb so strongly that they are produced overturn peak and which has relatively small peak at the multiple of the fundamental vibration frequencies. Infrared spectroscopy of hydrocarbon. Hydrocarbon contain only carbon-carbon bond, carbon-hydrogen bond, and infrared spectrum does not provide enough information to identify a structure conclusively. But the absorption of carbon-carbon and carbon-hydrogen bond can indicate the presence of double and triple bond. Carbon-carbon bond stretching. Stronger bond generally absorb at higher frequency because of their greater stiffness. Carbon-carbon single bond absorb around 1200 centimeter inverse. Carbon-carbon double bond absorb 1660 centimeter inverse. Carbon-carbon triple bond absorb 2200 centimeter inverse. At As discussed for the octane spectrum, carbon-carbon single bond absorption are not very reliable. We use fingerprint reason primarily to confirm the identity of an unknown compound by comparison with authentic spectrum. The absorption of carbon-carbon double bond, however, are useful for structure determination. Mostly unsymmetrical substituted double bond produce observable stretching absorption in the region of 1600 to 1680 centimeter inverse. The specific frequency of double bond stretching vibration depend on whether there is another double bond nearby. When two double bonds are one bond apart, they are said to be conjugated. As we see in previous chapter, conjugated bonds are slightly more stable than isolated double bond because there is a small amount of pi bonding between them. This overlapping between the pi bond leaves a little less electron density in the double bond themselves. As a result, they are little less tough and vibrate a little more slowly than an isolated double bond. Isolated double bond absorb around 1640 to 1680 centimeter inverse, while conjugated double bond absorb about 1620 to 1640 centimeter inverse. The effect of conjugation is even more pronounced in aromatic compound, which has 3 conjugation double bond in a 6-membered ring. Aromatic carbon-carbon double bond are more likely one and a half bond that's 2 double bonds, and they reduce pi bonding result in less double bond with lower stretching frequency around 1600 centimeter inverse. Carbon-carbon triple bond in alkyl are stronger and stiffer than carbon-carbon single or double bond, and they absorb infrared light at higher frequency. Most alkaline triple bonded atoms have stretching frequency between 2100 to 2200 centimeter inverse. Terminal alkyl usually gives sharp stretching between carbon-carbon triple bond single of moderate intensity. The carbon-carbon triple bond stretching absorption of an internal alkali may be weak or absent, however, due to the symmetric or the distributed triple bond with a very small or zero dipole moment. IR spectra of hydrocarbon. IR spectra of hexane, hex-1-ene or cis-octuene. The hexane spectrum is similar to that and octane. The CH stretching frequency from a band between 2800 to 3000 cm inverse, and the band in the fingerprint region is due to the bending vibration. The spectrum similarly indicate the absence of any IR active functional group. The spectrum of hex-1-ene show additional absorption characteristic of a double bond. Thus, carbon hydrogen stretch as 3080 cm inverse corresponding to the alkene carbon double bond CH bond involve sp2 hybrid carbon. The absorption at 61642 cm inverse result from stretching of carbon double bond carbon. The spectrum of cis-octuene in double bond has a very small dipole moment. Comparison of IR spectra of hexane, hex-1-ene, cis-octuene. The most characteristic absorbed in the hex-1-ene spectra are carbon-carbon double bond stretch at 1642 cm inverse. The unsaturated double bond carbon S stretch at 3080 cm inverse. The nearly symmetric double bond in cis-octuene give weak carbon-carbon absorption bond at 1660. The unsaturated double bond CH oct for ine. Comparison of IR spectrum oct-1-ene one ion. The IR spectrum of one ion show characteristic absorption at 33,313 cm inverse and at 2119 cm inverse. We cannot tell that oct4 ion is an alkyne from IR spectra because it displays neither the characteristic absorption seen and there is no alkynyl triple bond CH bond, and its symmetrical substituted triple bond has too small a dipole moment to produce carbon-carbon triple bond stretching absorption seen in the spectra oct1 ion. For each hydrocarbon spectrum, determination whether the compound is an alkane, alkene, alkyne, an aromatic hydrocarbon and assign the major peak above 1600 cm inverse. More than one unsaturated group may be present. Characteristic absorption of alcohol and amine. The OH bond of alcohol and NH bond of amine are strong and stiff. The vibration frequency of OH and NH bond therefore occur at higher frequency than those of carbon hydrogen bond. Alcohol OH 3300 cm inverse, acid OH 3000 cm inverse, amine NH 3300 cm inverse. Here is a graph. Saturated CH streak, NH stretch, spike. Characteristic absorption of carbonyl compound. Because it has a large dipole moment, carbon double bond oxygen bond produce intense IR stretching absorption. Carbonyl group absorb at frequency around 1700 cm inverse, but the exact frequency depend on the specific functional group and the rest of the molecule. For these reasons, IR often is the best method for detecting and identifying the type of carbonyl group is an unknown compound. To simplify our discussion of carbonyl absorption, we first consider the normal stretching frequency for simple ketone aldehyde and carbolic acid. We examine the type of carbonyl group that derived from the frequency. Simple ketone aldehyde acid. Carbon oxygen stretching vibration of simple ketone or carboxylic acid occur at frequency around 1710 cm inverse. Aldehyde at little higher 7725 cm inverse. The frequency are higher than those of carbon-carbon double bond because carbon-oxygen double bond has stronger and stiffer. Carbonyl absorption may be so intense that they produce small overtone peak around 3400 cm inverse, double their fundamental frequency. Heptane-2 on butyraldehyde. Infrared spectra of Hep2 on butyraldehyde, both the ketone and aldehyde show intense carbonyl absorption near 1720 cm inverse. In the aldehyde spectrum, there is two peak 2720 and 2820. Characteristic the aldehyde carbon hydrogen stretching. Hexanoic acid. IR of hexanoic acid. Carboxylic acid show a broad OH absorption from frequency 2500 to 3500. The broad absorption give the entire carbon hydrogen stretching region a broad appearance, punctuated by sharper carbon hydrogen stretching absorption. Functional group in the common having IR spectrum. Functional group in each has major peak above 1600 cm inverse. These are some Resonance lowering of carbonyl frequency. We saw that conjugation of carbon-carbon double bond lower its stretching frequency. This is also true of conjugated carbonyl group. Delocalization is the pi electron reduce the electron density of carbonyl double bond, weakening it and lowering the stretching frequency about 1710 cm inverse to about 1685 cm inverse for conjugated ketone, aldehyde and acid. Carbonyl absorption above 1725 cm inverse. Some carbonyl group absorbed at frequency higher than 1725 cm inverse. For example, simple carbolic ester absorb around 1735 cm inverse. These higher frequency absorption are also seen in strained cycling ketone, as shown there. Absorption spectra for butyl. The nitrile double bond stretching absorb at a slightly higher frequency than those of alkyl triple bond. Compare the spectrum of butyl with that of oct-1 ion. Carbon-nitrogen double bond absorbed in the same region as carbon-carbon double bond around 1660 cm inverse. However, carbon-nitrogen double bond gives rise to stronger bonder absorption because of greater dipole moment. The carbon-nitrogen double bond stretching often resemble a carbonyl absorption in the infrared spectra for three common compounds are provided. Each compound had one or more of the following functional group: conjugated ketone, ester, amide, nitrile, alkynes. Determining the functional group in each compound are assigned in the major peak above 1600 cm inverse. Summary of IR stretching frequency. Frequency 3300 for alcohol, amine, amide, alkyne. 3000 alkane, alkene acid. 2200 alkyne nitrile. 1710 carbonyl. 1660 alkene imyl amide. Thank you.